So let's go ahead and get started. So today we're going to be continuing where we left off with vectors. So we have quite a few clicker questions over vectors, and then we have a worksheet that we're going to go through after that. So first clicker question of the day. So scalars are typically numerical values, and vectors are quantities represented pictorially by an arrow with a specific magnitude and direction. So we want to choose from this list of options which one or ones of these are vectors. Okay, so go ahead and take a couple minutes and talk to your neighbor to figure out which of these is a vector. Yeah. Channel's 23. So for the whole semester, the channel is going to be 23. Polling's closed. Polling is closed. Why is polling closed? Oh, you know what? I might not have put an answer in for this one. That's probably why. Oh, that first one, I lied. It's not actually a clicker question. Or what did I do? Let me see what I did. Okay. I lied. The first one's not actually a clicker question. It's the next one. I meant to make this a clicker question, but I didn't. So already off to a great start, right, guys? Okay. But talk about this one, and then we'll talk about it afterwards. So this one was pretty easy to start out with, so let's go ahead and talk about it. So somebody from over here, what'd you guys say? C. Why C? It
has magnitude and direction.
It has magnitude and direction. So you look at all of these, like the first one, 5 seconds, there's no direction with time. 20 miles per hour in a school zone, no direction. C, 70 miles per hour north to Michigan. That's the only one here that has a direction. So C is the correct answer. All right, let's move on to the next one. So now we're getting into some rules for vector operations. So this question says consider 3 vectors, A vector, B vector, and C vector. How does the resultant of A vector plus B vector plus C vector compare to the resultant C vector plus B vector plus A vector? And as written, this is a little bit abstract, but what you can do is you can draw on a piece of paper just some vector A, some vector B, some vector C, and then see what happens when you add them together in this varying order. Okay, so go ahead and take a couple minutes to try that. Okay, so let's see what we have on this one. Okay, so predominantly we're saying C, but we want to understand exactly why the answer should be C. And so there's kind of 2 different ways that we can approach this. Somebody want to offer a suggestion for how we would go about proving that this is true? How might we prove it's true? Yeah.
Well, I thought of it more mathematically. I'm thinking if you have negative numbers and positive numbers, it doesn't matter in what order you add them because you're just adding, not subtracting anything. So it's going to make the same answer.
Good. So that's a good way to think about it. So let's consider some sample vectors that we're writing algebraically. So some vector A could be +4 x hat minus 5 y hat. Vector B could be equal to 2 x hat. And actually the notation we've been using is I hat and j hat. So let's do I hat, j hat, I hat, +3. Man, this chalk is not great today. +3 j hat. C is equal to -1 I hat minus 2 j hat. So if we want to add these together algebraically, it doesn't matter if I start with A and then add to B to it and then add C to it, because the numbers, addition's commutative, right? 2 plus 4 is equal to 4 plus 2, right? So that's one way to look at it. What's another way that we could think about this question?
Graphically?
Graphically, perfect. So what if I did the same thing? I made up some vectors. So let's make up some vectors. So some vector A, I'm going to choose to look like this. Some vector B, I'm going to choose to look like that. Some vector C, I'm going to choose to look like, the simplest one would be like that. Okay, so let's see what it looks like if I do A plus B plus C. So A looks like this. B looks like this, C looks like this, and so A plus B plus C is going to be the vector that starts where A starts and it ends where C ends, okay? Well, now let's see what happens if I do C first. So if I do C first, then it's going to look like this, and then this, and then this, and again, this resultant vector that I have here looks the same as the resultant vector here. So we're able to prove this two different ways, okay? Any questions about this? Okay, so let's look at something a little bit different. Should I keep the same question twice? No, this is the same question. It's commutative law. Wait, how many times did I copy the same question? Okay, there we go. So, just one note here, and this has to do with the fact that adding vectors is commutative in the sense that it doesn't matter what order I add them, and I could do A plus B, this is equal to B plus A, and associative in the sense that if I put brackets around this and I add A plus B first, that's the same thing as adding B plus C first. Okay, so these are just some rules for vector addition. Okay, now, next one. Now we want to think about what's going to happen if we have A plus B plus C versus A minus B plus C, and what we can say about this situation. So go ahead and talk about this one for a couple of minutes. So let's go ahead and talk about this one. And where we're going to begin with this is to go back to the same definitions for the vectors A, B, and C that we had in the last problem. Now, the only other thing that we need to add to our story here is to think about what the vector minus B is. And actually, I wrote this here already, but let me erase it and talk about it as I write it. So what we're interested in is comparing A plus B plus C to A minus B plus C. And so in order to do that, what we need to know is what minus B means or what it looks like. And so one thing that we can do is we can say that A minus B plus C is really the same thing as A plus minus B plus C. And so then the question is, well, what does minus B look like? Well, we can see algebraically if we come over here and multiply B by -1, right? So we multiply this whole thing by a negative sign. And so that makes this negative, it makes this negative. So it flips it. So if B was pointing like it is here, that would take minus B to look like this, okay? So that's what minus B looks like. And so now what we want to do is we want to investigate what A minus B plus C looks like. We already know that A plus B plus C is going to look like this, okay? So what I have in the blue here is A plus B plus C. And now what we want to do is look at what A plus minus B plus C looks like. And so if we do that, this is A. Okay, so I think this one was pretty easy, so let's move on from it pretty quickly. So what do we think? What do we think the answer was here? B. I have to read what B is. The resultants are different magnitudes but same direction. Good. Now let's see specifically why this is true. Now I redrew my vector A, my vector B, and my vector C, and if I want to do A plus B plus C again, this is the same thing as doing this, right? And so that's how we got this one. Now I might not have left myself enough room, but if we want to do 3 times this, so 3 times A plus B plus C, this is like taking this vector and stretching it out by a factor of 3, so it makes it really long like this. And then do the same thing with B. All right, this isn't to scale because I'm running out of room here. But you're scaling all 3 of these. And so when you multiply some vector by a scalar, you're either stretching it out or you're compressing it, right? So what would be an example of compressing the vector? This is an example of stretching it.
Like 1/2?
Yeah, multiply by a fraction, right? So if I multiply this by a half instead of multiplying it by 3, that kind of scrunches this vector down. Okay? Good. Good. Okay. and this is just a statement of scalar multiplication in vector addition, that the effects of the magnitude of the vector, you can use the ordinary arithmetic rules. So if I was to take 6 and multiply it by 3, I know that that's going to be 3 times the size of 6. And so it's the same thing with vectors. That if I multiply it by a number, it scales it the way that I expect it would. Okay. Now we talked about some of these already, but let's go ahead and go through this one kind of quickly. So we're giving you this vector E here, and we wonder what does, which one of the 4 of these options best represents minus E. Okay. All right, so I might have to ask harder questions moving forward. I think you guys are getting pretty good at this, but we realize here that when we look at these vectors, the vector E is pointing to the right. We talked about how when I negate that vector, I multiply it by -1, it just flips it. So it goes the other way. So this means that the answer should be number 1. Okay. Got one more of these, and then we'll get into our worksheet. How about this vector A? What does minus A look like? And I think these have gotten kind of trivial at this point, right? We know how to multiply vectors by -1 now. We're just flipping A, and so flipping A takes it from pointing up like this to pointing down like this. Okay?